So last time we justified this concept for Hall's marriage theorem of when we look at subsets of X that we're trying to match onto Y, if our subset of vertices that we're trying to match has too few things that it's trying to go to, then we can't find a match. And Hall's marriage theorem says that this isn't just necessary, it's also sufficient. So let's prove this. We're going to prove, so it's an if and only if statement, so let's just do both sides. So if the number of things in A is strictly greater than the number of neighbors of A for some subset A in X, then we cannot match all of A. Right? There are not enough neighbors. So we're never going to be able to find a matching. So that shows that this condition is necessary. The interesting part is that it's sufficient. So let's do the converse. So conversely, we're going to suppose that the number of elements of any subset A is going to be less than or equal to the number of neighbors of A for all A subset of X. We're going to prove by induction. Okay, we're going to do induction on the, let's say, the size of X. Induction on, or the size of the graph. The size of G, which is some value N. Okay, so we need a base case. What's the base case? Well, if the size of X equals 1, then we just need an edge. Just need an edge. Which of course we have because it has to have at least one neighbor, right? So we're good there. So what's our inductive hypothesis? So the inductive hypothesis says the following. It says that if X prime, the size of X prime is strictly less than the size of X, okay? And we still have to have our condition that the number of A is less than or equal to the number of neighbors of A for all A that are a subset of X prime, then X prime has a perfect matching onto its neighbors. Okay, that's our inductive hypothesis. So here, I guess, let's just make this precise. We're doing induction on the size of X. Okay, so let's go with it. We're going to have two cases. So case one is going to be sort of a case that never really comes up, but it does come up in the example that we have. So I guess so much for never. It's going to be the easiest case. So let's suppose that the size of A is strictly less than the neighbors of A for all A that are subsets of X. So Hall's marriage theorem just has this weak inequality. It says less than or equal to, and I'm saying, okay, suppose it's actually strict all the time. That's the case here. This guy has 2. If you take these 2 together, they've got 3 that they're matched with. This guy's got 3, and so on and so forth. So this case actually holds for this graph. And for this graph, it's super easy to find a matching, and we'll see the case is the same here. So for this case, all we're going to do is pick any edge we want and kind of throw it out. So the idea here is just, okay, well then just, if we've got an abundance, just pair these guys up and then just do the rest by induction. Okay, let's see how that works. So we're going to say, let X be an X and pick Y, that's a neighbor of X. We know that a neighbor of X has to exist because, in fact, there's at least 2. So just pick one. And set G prime equal to G, and let's take away X and take away Y. Okay? I've deleted X and I've deleted Y. The idea of what I'm doing is I've said, okay, I'm taking this edge, and now I'm going to take those 2 vertices out of the game, and I'm going to look at what's left. Okay? Well, let's make sure that I was going to use the inductive hypothesis, but let's make sure that everything holds. Well, the size of X prime is strictly less than the size of X, so that's good. We need to check the marriage condition. So the size of any subset we know is less than, so here it's strictly less than the neighbors. That means it's less than or equal to the number of neighbors, and let me be specific, the number of G neighbors minus 1. Right? You can change a strict inequality to a weak inequality by subtracting 1. And now this is actually less than or equal to the number of neighbors in G prime of A. Why G prime? Because in G prime, I took away one vertex from Y, so that's that -1 here. So I have at least this many. So this means that yes, in G prime, Hall's inequality holds. So by the inductive hypothesis, we can match X prime onto Y prime. And so now we're done. So in this case, we just, we take out this edge here, and then by induction, we're done. But this was a very special case. And in fact, it used the weak inequality to prove it. So we definitely need to do the other case. So now what we're going to do is we're going to suppose we have some B that's a subset of X such that we have exact equality. So this is a common trick in doing these problems that we're going to run into, which is we have this idea of a weak inequality, and somehow it's easier to split it into, okay, strict or equal, because it just gives us more information, and there's more information to play with. So now we're in this case, and we're actually going to have two cases over here. So let me divide this a little bit here. So if B is exactly equal to its neighbor, it has exactly the right number of things to match it, okay? Then I'm going to let G1 be B union the neighbors of B. So the idea is that I'm going to take my B's here and suppose they exactly match up to these guys. Okay, I'm going to take those apart and I'm going to match those separately from what's left. Okay, can I always do that? Well, let's look. For A, that's contained in B, right? We know that the neighbors of A, the neighbors in G of A are actually equal to the neighbors in G1 of A, because A is contained in B and we've taken all of B's neighbors. So the inductive hypothesis applies to G1. So that's great. So that means that we can match G1. That implies we can match G1. So that's basically saying we can match B. And now let's consider what's left. So G2 is going to be everything that's left. It's going to be G minus G1. So that means for X, we take out B, and for Y, we take out all of B's neighbors. And again, we need to check Hall's condition. So we need to check for any C that's contained in what's left. So this is going to be contained in X minus B. We need to consider its neighbors. Well, we have the neighbors in G of C union B. We can think about those. So take C and throw in everything from B as well. This is equal to the neighbors in G of C disjoint union. So we often write it like this, and I'll just emphasize this is disjoint, the neighbors in G of B, right? And so we've actually thrown these guys out when we did the G2. So the number of the neighbors in G2 of C, right? This is going to be the number of neighbors in G2 of C union B minus the number of neighbors in G of B, which is greater than or equal to the size of C union B by the condition on G minus the number of B by the hypothesis of the case that we're in. So here, that's where I'm letting these be equal. And this is using the condition that I have on G, which is up here. Okay? But now we can add those up. So that is going to be equal to, because B and C are disjoint, this is the size of C. So yeah, the inductive hypothesis applies here as well, because here we have the neighbors are greater than or equal to the set. So we partitioned, for this case, we partitioned our graph into B and not B, basically. But here we had to take the neighbors into account. This was the easy case, and this case required a little bit of subtle thinking. But in any event, it does show us that Hall's marriage theorem is a perfect characterization of whenever we have a perfect matching in a bipartite graph.